Let's begin discussing the individual properties of logarithmic functions, and we'll begin with the zero exponent rule. The logarithm of 1 is equal to 0 since any number to a power of 0 is equal to 1. So we have log of any base b of 1 is equal to 0. If we change this from logarithm form to exponential form, it is a little bit easier to see why that is. When we do so, we'll take the base b and raise it to a power of 0. And any number raised to a power of 0 is equal to 1. So it doesn't matter what the base is. If you are finding the logarithm of 1, the answer is 0. So if the base were positive 1, for example, you would get 1 to a power of 0, which is equal to 1. If the base were 2, it would be 2 raised to a power of 0, which is equal to 1. So it doesn't matter what the base is. If you evaluate the logarithm of 1, it will be equal to 0. So this is one property of logarithms. Another property is the logarithm of 0. The logarithm of 0 is undefined since the base of a logarithm must be positive. The logarithm of any base of 0 is undefined. Why is that? It is because our base b must be greater than 0, and any number that is greater than 0 raised to a power will not be equal to 0. So log of base b of 0 is equal to some number y. If we change this to exponential form, we'll get our base b raised to a power of y is equal to 0. And if our base b is greater than 0, there's no number that we can raise to a power and wind up with 0. So if our base were 1, for example, 1 raised to a power of y cannot result in 0 no matter what we make y. If y were negative, this would turn to a fraction. If the base were positive 2, same thing. 2 raised to a power of y cannot be equal to 0. So keep this in mind. If you are finding the logarithm of 0, there's no base that will allow you to find a value for this. Another property is the logarithm of a negative value. And the logarithm of a negative number is undefined since the base of a logarithm must be positive. So since our base is greater than 0, there's nothing we can raise this number to that will result in a negative value. So the log of base b of some negative number is equal to y. If we change this to exponential form, it would result in our base b raised to a power of y is equal to negative 1. And this is not true because if b is positive, there's nothing we can raise it to that will allow it to then become negative. If our base were 1, there's nothing we can raise 1 to that would make it negative. If our base were 2, there's no value we can raise it to that would make it negative. So throughout this chapter, you'll notice that we will not be taking the logarithm of a negative value, and this is why. Now, let's begin reviewing the product rule. And there will be two different use cases in which you'll be using the product rule. You'll be using it to combine logarithmic terms, and you'll be using it to expand logarithmic terms. So we'll begin by reviewing how we use the product rule to combine terms. And the logarithm of the product of x and y is equal to the sum of the logarithm of x and the logarithm of y. So if we have the log of base b of x times y, that is equal to the log of base b of x plus the log of base b of y. Before we walk through examples of how to combine terms using this rule, let's actually first go through the proof of the product rule. So let's begin with our statement. Log of base b of x times y is equal to log of base b of x plus the log of base b of y. So how can we break down this statement to make sure that it is true? Well, let's begin by looking at the individual logarithmic terms here. And let's set our first log term, log of base b of x, equal to a variable m. And when we do so, if we want to change it to exponential form, we would have our base b raised to a power of m is equal to x, as we see here. And let's leave that there for a moment and do the same to our second logarithmic term here. So let's set log of base b of y equal to a variable n. And if we want to change this expression to exponential form, it would give us our base b raised to a power of n is equal to y, as we see here. Now, using these statements, we can now start back at the beginning, x times y, and work our way out to this statement here. So let's begin by multiplying x, which is b to a power of m, times y, which is b to a power of n, giving us x times y is equal to b to a power of m times b to a power of n. And since these have the same bases, we can combine these terms by adding their exponents, m plus n. And now that we've multiplied x times y, let's now take the log of base b of both sides of this equation here. And that would give us log of base b of x times y is equal to log of base b of b to a power of m plus n. Now, when we are taking the log and the base matches the base of the argument, these actually cancel each other out, leaving us with just the exponent, m plus n. That's called the inverse rule. We'll actually be reviewing that a little bit more in depth later in the chapter. But for now, just trust me that that is true. So that leaves us with m plus n. And now, since we have log of base b of x times y on the left side, we now want to take m plus n and expand it back out. Now, earlier we saw that m was equal to log of base b of x and n log of base b of y. So we can replace m with this term and n with this term, bringing us back to our statement. Log of base b of x times y is equal to log of base b of x plus log of base b of y. So now that we've proven the product rule, let's now take a look at some examples of how it works. Let's say we had a log of base 6 of 2 times 5. We can expand this term into two different terms. The first term would be log of base 6 of 2, which we see here, plus the log of base 6 of 5, which we see here. So these two terms can be combined to give us this term here, or this term can be broken up to give us these two terms here. Let's take a look at another example. Let's say we were given log of base 2 of 3 times 4. We can expand this into two different logarithms. The first one would be log of base 2 of 3, which we see here. Since we're multiplying these arguments, we will add the second log, giving us log of base 2 of 4. Now remember, with the product rule, the singular logarithm will have an argument where we are multiplying two numbers. And we can expand this into two logarithms that have the same base. And we are adding those logarithms. The first term has the argument of the first number, and the second term has an argument that is the second number in the original argument. Now we want to make sure that we do not confuse this for when we have a log of base b and in our argument we are adding x plus y. That does not equal the log of base b of x plus the log of base b of y. In the original logarithmic term, we need to be multiplying x times y, not adding them. Now, let's look at one use case in which we will use the product rule to separate certain logarithmic terms. A number can be separated into its factors in order to apply the product rule. So let's say we have a log of base 8 of 12. 12, our argument here, can be broken up into factors that produce a product of 12, such as 3 times 4. So log of base 8 of 12 is equivalent to log of base 8 of 3 times 4. As we just saw, we can use the product rule to separate this to log of base 8 of 3 plus log of base 8 of 4. So this is how we can use the product rule to separate a singular term by taking its argument and breaking it up into two factors, and then separating this argument that has two factors into a sum of logarithms of those two factors. The log of base 8 of 12 would also then be equivalent to log of base 8 of 6 times 2. These are also two factors of 12, so this can be separated into log of base 8 of 6 plus the log of base 8 of 2. And both of these expressions, log of base 8 of 6 times 2 and log of base 8 of 3 times 4, would both be equivalent to log of base 8 of 12. So you do have some flexibility in how to go about simplifying logarithmic terms. Now the product rule can also be used to combine two logarithms that have the same base into a singular logarithm. So the same way we can take this logarithmic term and separate it into a sum of these arguments, we can take these two logarithms and combine them since their bases are the same, and we do so by multiplying the arguments 6 times 2, and then we know 6 times 2 would be 12. So we can use the product rule to break up a term, or we can use the product rule to combine two terms to simplify it into a singular term. So that is the use case we are going to practice now. We're going to practice combining two logarithmic terms that have the same base by multiplying their arguments x and y to give us a singular logarithm of a base b of x times y. This is the same product rule we saw a moment ago, but we've now turned it around. We have the two terms on the left side, and we're combining it into a singular logarithmic term. So if we take the same example we were looking at a moment ago and turn it around, we would have log of base 8 of 6 plus log of base 8 of 2. And since we have two logarithms that are being added together and they have the same base, we can combine them into a singular logarithm by multiplying their arguments 6 and 2, giving us an argument of 12. But let's walk through a new example together from the beginning. Let's say you were asked to combine the terms and simplify if possible, and you were given log of base 6 of 2 plus log of base 6 of 18. So how would we go about combining these two terms? Step 1, we want to combine the logarithms by multiplying the arguments 2 and 18. So we keep the base 6. So that would give us a log of base 6 of 2 times 18. And 2 times 18 would be equal to 36. And now, this base can be multiplied times itself to give us this argument of 36. So that is the clue that we can simplify this term further. So we want to set log of base 6 of 36 equal to y. And now we can change this to exponential form, allowing us to solve for y. So when we want to change this to exponential form, we would have our base 6 raised to a power of y, and we want to set that equal to 36. And now we solve for y by multiplying this base 6 times itself until we get 36. And 6 squared would be equal to 36, letting us know y is equal to 2. So we find that log of base 6 of 2 plus log of base 6 of 18, which is equal to log of base 6 of 36, and this is equal to 2. So we use the product rule to take two logarithmic terms and to combine them into a singular logarithmic term. And then we were able to simplify that logarithmic term by converting it to exponential form, leaving us with a singular term, positive 2. And that is how we go about using the product rule to combine terms. Let's now have you try a few practice questions. Combine the terms and simplify if possible. Question number 1. Log of 4 plus log of 12. Question number 2. Log of base 2 of 13 plus log of base 2 of 3x. Question number 3. Log of base 4 of 2 plus log of base 4 of 32. And question number 4. Log of base 6 of 9 plus log of base 6 of 4. Pause the video, answer these questions, and then press play when you are ready to begin. Question number 1. We are given log of 4 plus log of 12. Since the base is not shown, they're actually the same. These are common logs. They have a base of 10. So they do have the same base, so we can combine these two terms. And we do so by multiplying the arguments 4 times 12. And 4 times 12 is equal to 48. So log of 4 plus log of 12 is equal to log of 48. So that is the answer to question number 1. Let's now have a look at question number 2. We are given log of base 2 of 13 plus the log of base 2 of 3x. So step 1, we want to combine the logarithms by multiplying the arguments 13 and 3x. And 13 times 3 would give us 39x. So we find that the log of base 2 of 13 plus the log of base 2 of 3x is equal to the log of base 2 of 39x. So that is the answer to question number 2. Let's now have a look at question number 3. We are given the log of base 4 of 2 plus the log of base 4 of 32. So step 1, we want to combine the logarithms by multiplying the arguments 2 and 32. And 2 times 32 is equal to 64. And since this base 4 can be multiplied times itself to give us the argument of 64, that is the clue that we want to simplify this term even further. So we'll do so by first setting this logarithmic function equal to y. So we have the log of base 4 of 64 is equal to y. And now we can change this function to exponential form. So we take our base 4, raise it to a power of y, and set that equal to the argument 64, as we see here. And 4 raised to a power of y is equal to 64 can be changed to 4 to a power of y is equal to 4 to a power of 3. By them having the same base, we see that their exponents are equal to each other. So y is equal to 3. And if the log of base 4 of 64 is equal to 3, that lets us know that the log of base 4 of 2 plus the log of base 4 of 32, which is equal to the log of base 4 of 64, is equal to 3. So that is the answer to question number 3. Let's now have a look at question number 4. we were given the log of base 6 of 9 plus the log of base 6 of 4. So step 1, we want to combine the logarithms by multiplying the arguments. 9 times 4. And 9 times 4 is equal to 36. And our base 6 can be multiplied times itself to give us the argument of 36. So that is the clue that we need to let us know that we want to simplify this further. So step 2, we want to set this logarithmic function equal to y. So we get log of base 6 of 36 is equal to y. And now we can convert this to exponential form. So we take our base of 6, raise it to a power of y, and set that equal to the argument 36, giving us 6 to a power of y is equal to 36. And we want to change 36 to its equivalent, 6 squared. And now that they have the same base on both sides, we see that their exponents are equal to each other, showing us that y is equal to 2. And if log of base 6 of 36 is equal to 2, that shows us that the log of base 6 of 9 plus the log of base 6 of 4, which is equal to the log of base 6 of 36, is equal to 2.